Hi, this presentation will discuss barycentric coordinates. It's a kind of linear interpolation on 3 points. Previous videos talked about linear interpolation with lerping on 2 points. We're going to generalize this in a fairly substantial way to 3 points. So the situation is the following. We have a triangle T in RS, S greater than or equal to 2, with vertices x, y, and z. And I will typically draw these triangles with x, y, and z in this positions, x, then y, then z. So here's the triangle T. And U is a point in the plane P containing x, y, and z, so containing the triangle T. If we write U in the following form, we can write U as U equals alpha x plus beta y plus gamma z, and this is an affine combination. So alpha plus beta plus gamma equals 1. And alpha, beta, and gamma are called the barycentric coordinates of U. And of course that's relative to the triangle T and the vertices x, y, z. The barycenter of a triangle means basically the center of the mass of the triangle. Barycentric coordinates is expressing U in terms of a weighted average of the x, y, and z if it's inside the triangle, or more generally as an affine combination of x, y, and z if it's in the plane containing the triangle. So let me just mention here, if U is inside T, including on the boundary, then alpha x plus beta y plus gamma z is a weighted average. And recall that weighted average means that alpha, beta, and gamma are all greater than or equal to 0. So we're going to talk on the next board about the existence of barycentric coordinates for a point U, and then in later videos we'll explain how to determine the barycentric coordinates for a point U. First, I'll state a theorem about the barycentric coordinates for the point U when it's inside the triangle. This includes being on the boundary of the triangle. So let T be a triangle with vertices x, y, z, and we're in RS, S greater than or equal to 2. Let U be in the triangle, and this can be either the interior of the triangle or on its boundary. Then U can be written as a weighted average U equals alpha x plus beta y plus gamma z, with alpha plus beta plus gamma equals 1, and alpha, beta, and gamma all greater than or equal to 0. So it's a weighted average. So let's give a proof of this. It's not a hard proof. We'll just do pretty much a picture proof, but a little bit of computation. So here's our triangle T with the 3 vertices x, y, and z. Here's our point U in the interior. So we start by drawing the line between U and Z and extending it to where it hits the edge x, y, and we call that intersection point W. First of all, we do have to rule out the case that U is equal to Z. So if U is equal to Z, then U equals 0x plus 0y plus 1 times Z. So U has barycentric coordinates equal to 0, alpha equals 0, beta equals 0, gamma equals 1. Otherwise, we assume U is not equal to Z. We form the line containing U and Z, and we let it intersect x, y at W. So let the line containing U and Z intersect x, y at W. Now W lies on the line, and we know that any point on the line joining x and y can be written with linear interpolation. So by lerping, from the previous videos, W equals ax plus by for some weighted average a and b, in particular some a, b greater than or equal to 0, with a plus b equals 1. And that follows by the fact that W is lerp from x to y by factor b for some number b in the range 0, 1. And remember, that's the same as 1 minus b x plus b y. So we have a equals 1 minus b, in other words, here. So now we do the same thing with U. Similarly, U equals CW plus DZ for some C and D greater than or equal to 0, with C plus D equals 1. And again, this is because U can be written as the form lerp W Z D. Okay, it follows from this that U is, we just substitute in the formula for W here, it's AC times X plus BC times Y plus D times Z. So we take alpha equal AC, beta equals BC, gamma equals D. These are the barycentric coordinates for U as desired. And notice that AC plus BC plus D equals A times C plus equals A plus B times C plus D, and that's equal to C plus D because A plus B equals 1, and that's equal to 1. Also, they're all greater than or equal to 0. A, B, C, and D are all individually greater than or equal to 0. So AC is bigger than or equal to 0, BC is bigger than or equal to 0, and D is greater than or equal to 0. And this proves the theorem. So the moral of the theorem is that if you have a point inside the triangle or on the boundary of the triangle, then you can write U as a weighted average of x, y, and z. The next theorem will deal with the case where U is in the plane containing the triangle, but not inside the triangle. So in this case, we have the same type of situation. X, Y, and Z are vertices of the triangle T. Now T lies in a plane P, and U is somewhere in the plane P, but not necessarily inside the triangle T. But the conclusion is that in this case, then U can be written as an affine combination U equals alpha x plus beta y plus gamma z. And what that means, of course, is that alpha plus beta plus gamma equals 1, but there's no requirement that they're non-negative. In fact, if you're outside the triangle, at least one of them will be negative. So we could actually rework the same proof that was on the previous board with a little bit of care. You could just make this exactly the same proof work. But I want to give a different proof just because it also helps to illuminate the ideas of what's going on here. So again, we've got our triangle X, Y, Z, and it's a triangle, it's a proper triangle, the points are not collinear. And we've been assuming throughout that the triangle is a proper triangle with not having collinear vertices. And we're going to look at the vector, since T is a proper triangle. We know that the following, the pairs of edges are not parallel to each other. In particular, what this means is y minus x and z minus x are linearly independent. So here's y minus x. Here's z minus x. Are those vectors drawn in red there? And they're linearly independent. So the plane P can be characterized in the following way. The plane P contains exactly those points of the form x plus beta times y minus x plus gamma times z minus x for beta and gamma constants, scalars, ranging over all possible constants, or all possible scalars, all possible real numbers. Because think of the plane, think of the x as if it were the origin of the plane. We've got two linearly independent vectors rooted at x, and you take x plus any linear combination of those two vectors, and you can get any point in the plane and exactly points in the plane like that. Thus, U has the form, U is equal to x plus beta y minus x plus gamma z minus x for some alpha and beta. Sorry, for some beta and gamma. If we let alpha then be 1 minus beta minus gamma, then we get U is alpha x plus beta y plus gamma z, because we've just got the 1 times x, beta times minus x, and gamma times minus x gives us the coefficient on x. And so this is, we have alpha plus beta plus gamma clearly equals 1, because alpha is 1 minus beta minus gamma. So this is an affine combination. So QED on this theorem as well. So in the next presentations, we'll talk about how to find alpha, beta, and gamma from U. But that's the end of this presentation. Thank you very much.